Okay. So last week we studied, how to analyze heat conduction. Okay. So this is pretty slow. So if you want to determine the rate of heat transfer by conduction, you can use this equation. So this equation was basically, that shows how the rate of heat transfer is related to whatever the heat transfer condition is. For example, it depends on the area, the cross-sectional area. The larger the cross-sectional area, the higher rate of heat transfer we can expect for conduction, and the larger the temperature difference, and shorter the distance, and of course, there is a material specific properties which is thermal conductivity. Some substances can transfer heat better than the others. So usually we use thermal conductivity K to show material's ability to respond to changes in its thermal environment. So that means how fast heat transfers in a material. So that's a thermal diffusivity. Where's the thermal conductivity? Oh, this one. A measure of material's ability to transfer thermal energy by conduction. And this is a material property, temperature dependent. And so if you have two temperature values between two positions, we use the average temperature to evaluate thermal conductivity. But unless there's a significant temperature differences, we usually do not care much about the temperature dependency of thermal conductivity. If you look at the figure on the left-hand side, it shows that the range of thermal conductivity values for different substances. Usually gases have very low thermal conductivity, and liquids have higher thermal conductivity, and usually pure metals have relatively higher thermal conductivities than others. Then what material has the highest thermal conductivity? Made of carbon, yes. Graphene, carbon nanotube. Heard about that, right? So there's a single word carbon nanotube, multi-word carbon nanotubes, whose thermal conductivity values are greater than 2,000 watt per meter Kelvin. If you have a graphene, which is similar to carbon nanotube, but carbon nanotube is a layer of graphite is making a tube shape that is carbon nanotube. If you take this one and make it a flat layer, that's a graphene, and whose thermal conductivity is greater than 3,000 watts per meter Kelvin. Okay. If you look at the figure on the right-hand side, you can see the temperature dependency of thermal conductivity values. Usually, K value goes up when temperature goes up. Similar to many other material properties, this one is also temperature dependent. It means these values change with temperature. What is the one of the most common the material properties that you can experience the temperature dependency of it? Viscosity. When you cook fried egg, what do? You pour oil on a pan, right? And you drop egg right away? No, you wait. And how do you know temperature goes up? You slightly shake your pan. You can see, the oil is moving faster than you guess that the temperature is high, because the viscosity goes down when temperature goes up, right? So those are temperature dependent properties. So thermal conductivity is a measure of material's ability to transfer heat. And there is another property which is thermal diffusivity. This one, thermal diffusivity, alpha, a measure of material's ability to respond to changes in its thermal environment. In other words, how fast it diffuses through a material. And many people, they get confused between thermal conductivity and thermal diffusivity. And one simple way to understand the difference between these two is, when do we use thermal conductivity and when do we use thermal diffusivity? The simple answer is, we use thermal conductivity in steady state heat transfer problems. On the other hand, we use thermal diffusivity in transient heat transfer problems. So steady state heat problems mean so let's talk about an example. Steady state heat transfer problem. One of the simplest steady state heat conduction problems is when we talk about heat loss from indoor space to the outside. So let's say that the temperature in this classroom is around 20 degrees Celsius. So this is indoor, and there's outdoor, and there's a wall dividing these two. And inside is 20 degrees Celsius. Outside, let's say it is near Christmas break, 0 degrees Celsius. Then the temperature distribution is going to be there are 4 temperature points. One is the temperature of the air inside this building, inside the wall, and inner surface temperature, outer surface temperature, and outside air temperature. So there are 4 temperature points. And let's talk about these 4 temperature points. What is the heat transfer direction? The heat transfer direction is, according to the second law of thermodynamics, heat transfer direction is from the highest temperature to the lowest temperature. So we know there's a heat transfer from 20 degrees Celsius to 0 degrees Celsius. That is heat transfer Q. And then, what kind of heat transfers are there? Just conduction. There are 3 heat transfers that we studied last Tuesday: conduction, convection, and radiation. Conduction, convection, and radiation. Conduction means pure heat transfer from one molecule to another adjacent molecule. And convection means when there is mass transfer. Usually between a fluid, air, and a solid surface. And radiation means when the heat transfer where there is no medium is involved, like a solar radiation. So in this case, there are 3 heat transfers. One, from the air to the inner surface. Air can move, therefore, this heat transfer is convection heat transfer. So there's a first heat transfer Q is going to be conduction heat transfer. And heat transfer from the inner surface of this wall to the outer surface of this wall, since it is solid, it is a heat transfer through a wall, and this wall cannot move, so it's going to be conduction. So the next heat transfer from the inner surface to the outer surface is going to be conduction. And there's one last heat transfer from the outer surface to the air outside. Since air can move, it's a fluid. So that's going to be mass transfer. So it is convection. So the last one is convection here. Now, we can think about surface energy balance that we studied last Tuesday. According to that, on a surface, any incoming energy transfer could be the same as outgoing energy transfer. So there are three heat transfers according to surface energy balance. Conduction heat transfer could be the same as conduction heat transfer. And this conduction heat transfer should be the same as convection heat transfer. So convection heat transfer, conduction heat transfer, convection heat transfer, they are all the same. Okay, so when I say the rate of heat transfer from the inside the classroom to the outside is, let's say, 2000 watts, that means this convection heat transfer from the air to the wall is going to be 2000 watts. Conduction heat transfer from this wall to the other side of the wall is also 2000. From that surface to the outside, the air is going to be also 2000. Then to maintain a constant temperature inside the classroom, what kind of heater do you need? A heater whose rating is 2000 watts. Then you maintain constant temperature, 20, inside. That's what happens in this classroom, right? Outside is cooler than inside, and there is a continuous energy loss from the inside to the outside. However, we maintain constant temperature because the heater is providing same rate of heat transfer. If the heat transfer from the building is greater than heat loss, then the temperature of this classroom goes up. If the heat transfer from this heater less than the rate of heat transfer through this wall, then the temperature of the air in the classroom goes down. So our assumption is that temperatures remain constant. Then it is called steady state. Steady heat conduction, heat transfer. When we have steady heat transfer, we use thermal conductivity K. Okay? Then let's talk about another example. So our assumption is that initially the temperature of the air in the classroom is 20. Temperature of the outside air, outside of the building, is 0 degrees Celsius. That was our assumption. Then it is a steady heat transfer problem. But what about that there was no heater was turned on in this classroom? So the temperature of the classroom, the temperature of the air in the classroom and the temperature outside the building should be the same when there was no heating here, right? So let's assume that we have the same heat transfer problem between indoor and outdoor. So previously we assumed that the heater was running for a long time, so our initial temperature of the air does not change, then it is a steady problem. But what if we turn the heater off and then leave the building for overnight, and the temperature inside and the temperature outside should be the same? Okay, that is the initial condition. Now, what is the heat transfer between air in the classroom and the what is the heat transfer between the air in the classroom and the air outside? There is no heat transfer because there is no temperature difference. According to the second law of thermodynamics, heat transfers only from a higher temperature point to a lower temperature point. When there is no temperature difference, there is no heat transfer. Then, now let's assume that we just turn on the heater, and therefore the temperature inside goes up first. Let's assume that, that we turned on the heater, so the heater suddenly increased the temperature of the air 20 degrees Celsius. Then what's going to happen to the temperature inner surface? The inner surface temperature was initially 0 degrees Celsius, and now the temperature is going to go up. It's going to move up from 0 degrees Celsius. Then there is a change in temperature. When there is a change in temperature, it is transient heat transfer problem. And when you have a transient heat transfer problem, we use thermal diffusivity alpha. Okay? So this thermal conductivity K shows material's ability to transfer heat. And this thermal diffusivity alpha shows how fast heat can transfer, so the temperature of the material can go up. Okay? So these two properties are one of the most widely used thermophysical properties in heat transfer. We use K in steady heat transfer problem. We use alpha in transient heat transfer problem. Okay? And how do we know one is a steady heat transfer problem and the other is a transient heat transfer problem? Always look at the temperature of the system. If the temperatures of the system remain constant, then it's a steady state heat transfer problem. When the temperature of the system changes, then it's a transient heat transfer problem. We have two different governing equations. We use one for steady state, we use the other for transient. We don't use one for both of them. Okay? So, after this chapter 1, we are going to study conduction first in chapters 3 and 5. So we are going to study conduction heat transfer. And this chapter 3 is going to be steady state heat transfer. Chapter 5 is going to be transient heat conduction. Steady state heat conduction, transient heat conduction. Once we study both of them, then you will have the second exam. The second exam covers these two chapters. Okay? That's for conduction. What about convection? There are 3 chapters, chapters 7, 8, and 9. So these are for convection heat transfer. So in chapter 7, we are going to study external forced convection, like the convection between a surface and a fluid that is moving. In chapter 8, we are going to study internal forced convection. That means we have a pipe or duct. We have fluid flows inside a pipe or duct. When there's a convection between, the material flowing and to the surface of the, the pipe, that's internal forced convection. And finally, free convection when there is no external force driving fluid flow. So these 3 are the chapters that will be covered by the final exam. Okay? So that is our plan for heat transfer course. Okay? That was the overview of what we are going to do. Then coming back to thermal conductivity and thermal diffusivity, both are material properties, so you can find them from a property table. Or you can calculate one from the other. The relation between thermal conductivity K and thermal diffusivity alpha is going to be, alpha is K over rho C. Alpha is K, this thermal diffusivity is K thermal conductivity divided by density times specific heat. The larger the thermal conductivity, the faster heat transfers into the material. Okay. So we studied there are steady heat transfer problem and there are transient heat transfer problem. How do we know a heat transfer problem is steady state or transient? And we learned there are 2 material properties. One is thermal conductivity that we use in steady state heat conduction. The other one is thermal diffusivity. We can use it in transient heat conduction. And we learned one equation that we can use to convert between thermal conductivity and thermal diffusivity. So those are the basics for heat conduction. Okay. Then what's next? There are 3 heat transfers: conduction, convection, radiation. So why don't we talk about convection heat transfer? Convection heat transfer is heat transfer between a solid surface and adjacent fluids that is in motion. So there should be mass flow. There should be mass transfer. So if the fluid does not flow, then that's not a convection. That is conduction. So you can use Free's law that we studied in the previous conduction. So again, just for your information, Free's law, the conduction heat transfer rate is minus Ka dt over dx. That's what we studied last Tuesday. If the surrounding fluids are not in motion, then we use conduction heat transfer. When the fluids are in motion, the amount of heat transfer due to the mass transfer of the fluid is greater than the pure heat transfer from one molecule of the fluid to the adjacent molecules. So we don't use the conduction equation anymore, and we use convection equation, which will be shown in the next slide. To understand convection heat transfer, we need to understand fluid mechanics. I'm pretty sure that you already studying or already have studied fluid mechanics. So let me just go over fluid mechanics. So one of the properties that we studied in fluid mechanics in terms of the parallel flow over a flat plate is boundary layer. So when there's a uniform fluid flow, and when we introduce a flat surface, what's going to happen is there is a force between the surface and the fluid. What is that force? Friction, right? Right? Imagine that you are walking. There's no friction. Then now you are going to touch this wall and trying to walk. Is it easy? No, because of a friction, right? So what happens when there's a friction occurs? There are two ways to understand fluid flow when there's a friction. The first one is when there's a slip. When there's a slip, when fluid particles are slipping on the surface. That is graduate fluid mechanics. In undergraduate fluid mechanics, we assume that no slip condition. That means that the fluid particles are going to be stopped at the surface due to friction. That is called no slip condition. So at the surface, fluid particles are stopped. Then what happened to the fluid particles on top of this stopped particle? The velocity is going to be slowed because there is a stopped particle. So initially, let's assume that the length of this arrow indicates the magnitude of the velocity, and right next to the surface, the velocity is going to be small. What about fluid particles on top of this one? This is already slowed particles. Therefore, the particle above is going to be also slowed, but moves faster than this one, about this much. And it's going to affect the fluid particles on top of it. And that's going to affect the fluid particles on top of it. And the same goes on, like that. And eventually, the fluid particles are at uniform temperatures when they are far away from the surface. So the region where fluid particles are slowed, that is called boundary layer. So the boundary layer forms like that. Our assumption is that the definition of the boundary layer is fluid particles within this layer has been affected by the friction from the surface. So those particles in the boundary layers are slowed. The velocities in these, the particles within the boundary layers are slower than outside the boundary layer. So here is called viscous flow, and outside is called inviscid flow. By the way, this is fluid mechanics. I haven't talked about heat transfer yet. So when we talk about velocity profiles of these fluid particles at a certain distance from the starting of this plate, then the particle, the fluid particle at the surface is going to be stopped, and there's a slight velocity increase like that. And once it goes outside of the boundary layer, we have a uniform velocity, same as here. So this is the boundary layer, and this is the velocity profile within a boundary layer. Once it goes outside, you have uniform velocity, the same as here. So if we assume that the velocity, the uniform velocity of the fluid is 10 meters per second, outside of the boundary layer, we have 10 meters per second everywhere. But within this boundary layer, we have 8 meters per second, 6 meters per second, 4 meters per second, etc., etc. And the velocity at the surface is going to be 0 meters per second. That is what happens in fluid mechanics. Similar here, we have a uniform velocity outside this boundary layer, 10 meters per second, but inside 9, 8, 7, etc., etc., etc. So that's what happened in fluid mechanics. What about in heat transfer? So our assumption, this one is prerequisite. So I guess you already know what happens in terms of fluid mechanics. If you're not 100% sure, that's okay, because each time I'm going to briefly introduce the fluid mechanics phenomenon whenever we discuss convection heat transfer, okay? Then what about heat transfer? The same thing happens, but not in terms of velocity. What is the main property in heat transfer? Density? No, temperature. So in fluid mechanics, velocity is the key property. So depending on the velocity at each location, we determine boundary layer. Similarly, in heat transfer, we use temperature. So let's assume that initially, each arrow, by the way, I say each arrow, the length of arrow indicates temperatures. The longer the temperature, the higher, and the longer the arrow, the higher the temperature, okay? So let's assume that it is 20 degrees Celsius. Everywhere is 20 degrees Celsius, like the air in this classroom. Now, if the temperature of this solid surface is at 20 degrees Celsius, then what kind of heat transfer do we expect? There's no heat transfer because there is no temperature difference, right? Heat transfer occurs from a higher temperature point to a lower temperature point. So let's have a different temperature value for the surface. I'm going to say the surface is at 100 degrees Celsius. So we are talking about this whiteboard, which is at 100 degrees Celsius. So it's pretty hot. So now I'm going to install a fan here, so blowing air in this way. So 20 degrees Celsius air is blowing over 100 degrees Celsius hot surface. That's what happens, okay? Then what do we expect? This one is at high temperature. So air is at low temperature, so we expect there is a heat transfer because there are temperature difference. From where to where? From 20 degrees Celsius to 100? No, the other way. From 100 degrees Celsius to 20 degrees Celsius. Because of this heat transfer, what do we expect? The temperature of the air goes up, right? But the temperature of the air somewhere here goes up first? No, the temperature of the air molecule, which is right next to the surface, goes up first. So initially, you can say it was 20 degrees Celsius at the beginning. Now, because of this heat transfer, it goes up quickly. Let's say 90 degrees Celsius. Here. But still, it takes time for the heat to transfer through. So outside, away from the surface, is still at 20 degrees Celsius. 20 degrees Celsius. 20 degrees Celsius. 20 degrees Celsius. Suddenly it is 90, and let's say 40 and 20. Then, while the areas are moving in this direction, there's more heat transfer going away from the surface. The 40 degrees Celsius air is going to hit the air molecule next to it. This 90 degrees Celsius air is going to hit the air molecule right on top of it. So this time here, 90, 80, 60, 40, and 20. Then outside of it, 20, 20, 20. Then there's a continuous heat transfer in this direction, right? While the fluid particles are flowing this way. So 90, 80, 60, 40, and 20 here. Then outside is 20, 20, 20, 20. So the layer whose temperatures are different from the initial temperature, outside temperature, that layer is called boundary layer. So if we talk about temperature profile, outside of this boundary layer, we have a uniform temperature 20, 20, 20, 20, 20, 20, 20. And once from this point, we have increased temperatures. And at the bottom, we have the highest temperature, 100 degrees Celsius. What about here? 20, 20, 20, and we have increased temperatures. And at the surface, we have the highest temperature, 100 degrees Celsius. So this is the temperature profile at a distance x from the starting position. This is the temperature profile. And this is the boundary layer where fluid particles are at different temperature from outside. Then this is boundary layer, this one, and this is boundary layer. Both of them have the same name. Then it's going to be confused, so we use different name. This layer, in terms of velocity, is called velocity boundary layer. That's fluid mechanics. This layer is called thermal boundary layer. And here we use conservation of momentum equation. Here we use conservation of energy equation. So now, let me ask a question. Yes. Oh, what time is it? Yeah, for the remaining 20 minutes. So give me 5 more minutes. Okay, we still have time, right? So, but the point is, the key point about convection is this one. So if you look at this one, do you think that it is easy to, solve? Not really, right? Now, this one, even more complicated. Can you solve it analytically? Or very simple with a lot of assumptions. So in reality, solving this phenomenon analytically is practically impossible. So what do? We use experimental feeding. We use, the correlations developed from experimental values. So those are the things that we are going to study in chapters 6, 7, 8. But if we get a value from an experiment, every experiment is different, right? What about if I perform an experiment for this whiteboard? Can I use it for that wall? Can I use it for the second floor? Not really, because they all have different dimensions. They all have different properties. Maybe this one is smooth, that one is rough. What about the carpet? What about the ceiling? So if we use, a correlation developed from an experiment, we need to come up with 10,000 or 10 million different equations to solve convection problems. So what do? There was one chapter that you studied in fluid mechanics, dimensional analysis. Do you remember that? That's what we are going to use to solve this one. Instead of thermal conductivity, instead of, the convection heat transfer coefficient, instead of, the actual, the property, we use dimensionless number to understand heat transfer by convection. That's what you did in fluid mechanics class. You remember Reynolds number. So we have many heat transfer dimensionless numbers. So we are going to study them first, and we are going to come up with a governing equation using those dimensionless numbers, and we are going to solve these dimensionless numbers, and later we are going to get the actual property from the dimensionless number that we got. So the convection heat transfer study is going to be in this form. We have a actual geometry, velocity, and etc., and we are going to convert everything into a dimensionless number and then solve the governing equation that is from an experiment, which is correlations. Then, return back to, convert them back to the actual properties. So that is how we solve convection heat transfer problems. Okay, I'm just giving you a brief introduction about what's going to happen, and because this is an introduction, chapter. Okay, and the main equation that we are going to use for convection is called Newton's law of cooling. So we have a rate of heat transfer or heat flux, that we are going to talk about heat flux later. By the way, heat flux is just the rate of heat transfer divided by surface area. And this H is heat transfer coefficient, which is the key property that you need to determine by studying chapters 7, 8, and 9. Multiplied by temperature difference. So that is the governing equation in convection heat transfer. So depending on H, we have a different convection heat transfers. So do you remember, that I told you that, that there was a comparison between jumping into a boiling water or going into a dry sauna. You remember that, right? You cannot survive when you jump into a, the boiling water. But if you walk into a dry sauna, which is at even higher temperature than the boiling temperature of water, you can survive. Why is that? This H for gas is very small, but H for liquid water is extremely high. So even the small temperature difference, you can receive a significant rate of heat transfer. Those are the things that we are going to study later when we go to chapter 7, 8, and 9. The next one is radiation, but since you don't have time, so we are going to continue this radiation, the slide after the exam. Any question about chapter 1? Nobody is interested? Everyone is interested in about review for exam 1? Okay, so that's everything. I'm going to stop recording here.